In this video, I'm going to go over the formation of acetals, which are an important type of reaction with ketones and aldehydes. So like with the formation of hydrates, acetals will more easily form with aldehydes than they will with ketones, but they can react with both. So an acetal has the general structure of this. So you have either an R group or a hydrogen, two of those, and then you have two acetal groups. And the acetal groups, right, they're coming from alcohols. Right, so in the formation of an acetal, we react an aldehyde or a ketone reacts with an alcohol. Now notice we have what looks to be two alcohols that have been added on. So you need either two alcohols as reactants or, a reactant that looks like that has two hydroxyl groups on it. And you'll see we'll use this reactant for one of the common reactions to form acetals. Now another note is, unlike the formation of a hydrate, acetal formation occurs only in acidic conditions. The reason being, if you're starting with, either here, we'll just do formaldehyde, right? We know that reacts well. Installing an R group onto that oxygen is going to be difficult, right? I mean, you think you could protonate it, and then if it acts as a leaving group, but the problem is it's not going to be a very good leaving group, given it would be leaving as, hydroxide, right, which isn't a good leaving group. So that's the reason when we go through the mechanism, it's going to be through an acidic condition. All right, so what is the mechanism? So for the reactant, I'm going to use an aldehyde, not formaldehyde, but I'll use an aldehyde here. So step one, all of the steps in this are going to be in equilibrium. So step one, I'm going to react it with a strong acid. The most common strong acid used is just going to be sulfuric acid because it's strong, and then it's non-nucleophilic and it's not basic, right? So it's going to be a good, or its anion isn't a good nucleophile, isn't going to work well. So that's the reason we'll use the sulfuric acid. So we've protonated our carbonyl oxygen. Step two, our alcohol is going to come in and attack now. I'm going to use ethanol here. So ethanol comes in. And remember, this ethanol still has the proton on it, so it's going to have a positive formal charge. Then my next step will be deprotonating and getting that hydrogen away. Now for the reagent, I'm going to put in here ethanol as what's deprotonating. Often in these reactions to form the acetals, since you're using alcohols, the solvent is going to be an alcohol. And if the solvent's the alcohol, that's likely what's going to react to deprotonate it. So oxygen comes in, can deprotonate, and then you're left with your first, not product, but it's an intermediate in this reaction. This right here is a hemiacetal. Right, called hemiacetal because we've gotten our one OR group on, right? This would be our one OR group, but then we still have an alcohol or an OH group on here, right? So we need to get rid of that OH group and get it to an OR group as well. And then we'll have our acetal. So we'll be in equilibrium again, and it's going to be the same step that we had as our first one. Strong acid, so in this case sulfuric acid, can protonate the hydroxyl group. So now I've got a good leaving group. So the electrons from the, I guess, ether, you could call it, right, are going to come down to form a double bond, kick off the water. So now we've reformed a carbonyl. We reformed a carbonyl. The next step, ethanol, is going to come in as the nucleophile. And we'll get very close to the final product we're looking for. We just need to deprotonate the ethanol that we've just added on. So for the deprotonation, this could be either water or an ethanol. So I'm going to put ethanol here again just because we have more ethanol in here than water if we're using ethanol as a solvent. And I'm left with my final product of the acetal. So that is my acetal. So the mechanism's not complicated per se because it's mostly just proton transfers. So these are all steps you've seen before. It's just you have to get the order of the steps right and understand what's going on with each step. So I want to break down this whole reaction to form the acetal into 2 parts and then the 7 steps overall. So part 1, this is going to be the formation of the hemiacetal. There are 3 steps in part 1. Right, we have a proton transfer. Step 2 is nucleophilic attack. And then step 3 is another proton transfer. Right, so step 1, proton transfer. Step 2, nucleophilic attack. Step 3, proton transfer. And then we form our hemiacetal. So then part 2 of the reaction is going to be the formation of the acetal. So the 4th overall step is another proton transfer. This one with the sulfuric acid, or a strong acid. Step 5 is going to be the loss of a leaving group. Right, we lose water in step 5. Step 6, nucleophilic attack. Ethanol comes in, in step 6. And then finally, step 7 is a proton transfer. So we finish it off with that proton transfer. This will be the same process for the formation of every acetal, whether your alcohol, you're using 2 alcohols or you use an alcohol like this one. It's always going to be 7 steps, and it's always going to be the same 7 steps. Something that can also make this simpler. The first step and the last step of each of the 2 parts is a proton transfer, right? So 4 of the 7 overall steps of this mechanism are just proton transfers. Then you have 2 nucleophilic attacks where you add the 2 OR groups on, and then you lose your 1 leaving group, which enables you to get rid of that water so you can form the acetal rather than staying at the hemiacetal. So I really recommend following these 7 steps, getting them down, because then any of these reactions of acetals will be simple for you because you know what the 7 steps are. The last note about the acetals is they can be used as protecting groups. So this would be important when, say, you want to not have one of your ketones react or your aldehydes react. If you have multiple carbonyl functional groups on a compound, but you don't want both to react, you can protect it by adding in an acetal, and then you can just take that acetal group away with water. So it's not a very difficult addition and then removal of a protecting group. So the mechanism, again, is going to follow those same 7 steps. I'll write it out here again, because this time we're going to be using a diol, right? And one compound that has 2 hydroxyl groups on it. So say I've got this ketone here. Step 1 is going to be protonation using the strong acid. My second step is going to be nucleophilic attack. So this time, that is my nucleophile. Another important thing, make sure you don't lose track of the carbons. It can be easy at one point to lose the 2 carbons in between the alcohols and only put 1 carbon in between, so make sure you keep those carbons there. Then I'm going to have deprotonation. In this case, I'll write it diagonally so I have the room. It's probably, I'll use water in this case because we'll have water floating around as well. But again, if you used the alcohol instead to deprotonate, that would work as well, because that could happen, right? The alcohol is floating around just like the water is. Right, so this is now my hemiacetal. So the next step, if you remember, is going to be protonation with a strong acid. And I'm protonating the hydroxyl group that's bonded to the ring. So one of the lone pairs from that oxygen is going to move down, kick off that OH2 group now, right, the water. So I've reformed a carbonyl. Now nucleophilic attack, this is going to be an intramolecular nucleophilic attack. Right, so then the last step is just going to be deprotonating. I'll use water again. And now I'll be left with my ketone that now has the protecting group on it. What am I protecting from? Right, I'm going to be protecting from, a nucleophilic attack with a Grignard, something like that. So if I were now to, say, put in a Grignard, so methyl magnesium bromide or something, I would get no reaction. Right, the Grignard doesn't have anything to attack there. All there are is sp3 hybridized carbons and oxygens that are not protonated, right? So there's going to be no reaction that's going to be taking place there. So that's how the protecting group works. If I want to remove the protecting group, I react with water, and I can kind of go in the reverse direction, right? All of this is in equilibrium. So if I add in water, I can just go in the reverse direction of this and get back to my ketone. So this is one of the most important uses of the formation of an acetal, is that we can use the acetal as a protecting group.